removal. Thanks for the nice introduction of Professor Tong. Actually, because the previous speaker did not come today, so I was moved from the last one to here. I hope I can save more time for the dinner. So today I will introduce some research progress on the CDI for the removal of organophosphorus compounds. So my main content mainly contains 5 parts. First is the background. As we all know, China is the most biggest and important industrialized country in the world. So every year, a lot of water in China was used for the industry. Meanwhile, a lot of industrial wastewater was also discharged. So as we all know, China, a lot part of China still lacked of the water resource. So the reuse of this industrial wastewater is very important. One of the ways is mainly used for the circulating cooling water. But during this process, the organophosphorus pollutants such as the HEDP and other compounds was usually added as the scaling inhibitor. So which we need to pay more attention on this pollutant. As a kind of the chemical stable and higher resistant to the biodegradation compounds, the conventional used methods such as biodegradation and the memory separation showed a low efficiency for these compounds. On the other way, this organophosphorus compounds usually show a negative charge because they contain a phosphonate group. So we want to know whether we can use some electrode driving method to remove or degrade this pollutant. As we all know, CDI can be used for the removal of charged ions. In this process, it usually have anode and electrode. During the charging process, the different ions can be collected from the different sides, while during the discharging process, we can just recover or separate the aimed pollutant. And in this way, we try to use it for this process. The electrode materials is the most important thing in the CDI. It usually can be divided into two different kinds. First is the AC and CNT and other EDL materials. It is used for the removal of ions, mainly based on the electron interaction. Yeah, another kind is the ferritic materials. During these materials, we need to achieve the ion exchange during the adsorption. However, the usually used materials still meet some main issues. For example, this electrode usually face the co-ion efforts, which lead to a low adsorption capacity. Another kind is the ferritic effort. It means from the anode and the cathode, some hydrogen ions or the hydrogen group will produce in the different kind. So the lifetime of the electrode will be inhibited, which leads to a low operation stability. Besides, as an electrode driving process, it's mainly used for the moderate ionic strength solution, which also limited its application. So we want to try to solve these issues to expand the application of CDI. To achieve this problem, to achieve this goals, the IEM can have already been used in the CDI to form an MCDI system. During this system, we usually added the AEM and CEM on the anode and cathode respectively. In this way, we can achieve the separation of the different ions, and in this way to limit the co-ion effort. Besides, with this relative dense layer, the hydrogen ions and the hydrogen group can be rejected from the cathode and anode. In this way, to achieve the long-term operation. However, the memory-based methods also meet some problem. For example, the memory usually was quite with a higher price. Another is also with the memory falling risk. Besides, after adding this memory, its performance for the low ionic strength solution will be limited further. So inspired by this, we want to use a memory coating method. We just use the polymer to coat it on the electrode. We want to try to achieve some the two goals. So to achieve this problem, we first use the two-line MCE. During this process, we mainly added the positive group, polymer group on the anode to form an MCE. And while on the cathode side, we added some negative group to form a C and MCE. So for the optimization, we first use the SAC as the guideline to say which kind is better. During the anode and cathode optimization, we try to investigate the effect of the different concentration of GA as a cross-linking agent. And also we use the different temperature to say the best condition for the preparation. After the modification, we found that when we use a relative low concentration of the cross-linking agent, the CDI system will achieve a better CAS. So for the characterization, we found that if the concentration of GA increased, it will lead to increased hydrophobicity. Moreover, the point of zero charge will move for the left, which means it was less resistant to this process. Besides, we also investigated whether the temperature is important in the cross-linking, and during the higher temperature, we did not add the cross-linking agent, while just in the low temperature condition, we added the GA as a cross-linking agent. From the functional group, we can see that there is no obvious the difference was observed. So we use this low temperature because we think it will be more easier and maybe more stable. So then we use when we prepare these two different materials, we establish three different systems. In the first one, we just changed the cassette in the system, and in the second one, we just changed the anode in the system. While in the third one, we changed both the acid and the cassette. And we found if we change both of them, the performance will be the best. However, if we only change the anode, it also showed quite good performance, especially during the long-term operation. You can find it's almost stable as we changed in the both anode and cathode. So in the future work, we just change the anode materials. So then we use the different voltage to see what will happen. Because for the organophosphorus, we not only want to achieve the separation due to its different charge, we also want to see whether we can use the correct redox reaction during the CDI to achieve the degradation of this compound. So we use the low voltage and a higher voltage. We can see if we did not added the memory coating layer, both of them can be used for the low voltage. But if the voltage increased surpasses the 1.2, we can see the conventional use, the ACF, showed a very obviously reduction during the long-term operation. While if we added the MCE coating on the anode, it will be more stable. And to further investigation the mechanism, we found this was mainly because without the protection of the membrane coating layer, the ACF was quite a bit easier to be oxidized during the process. We can see the content of oxygen increased very obviously. While adding this, this increasement degree will be decreased. So from this way, we can achieve the higher SAC for the CDI. But another issue for the CDI is it only can be used for the moderate ionic strength, while it was not suitable for the low or higher ionic strength. To achieve this problem, we want to further investigate a 3-layer MCE. Besides the polymer coating, we added a CNT layer while the electric spinning. When we use this way, it formed a 3-layer as the CNT, as the AC, CNT, and membrane coating layer. From morphology, we can see the previous AC was just separated one by one. If we added the CNT, we can connect them together to increase its electricity property. Besides, after the addition, after it as an interlayer, the formed CNT and MCE showed a more rough and a more porous structure. The further BET result, we can see even the CNT MCE was a little lower than the AC. The increase of it was more obviously than the MCE. Especially, it showed more the mesonopore dominant structure. Then we use it for the ion separation from the low concentration to the higher concentration of the fluoride. We can see when we compare with the AC and MCE, this CNT and MCE showed the highest SAC from the 100 ppm to 1050 ppm. This was mainly because with this loose structure, we can elevate the EDL overlapping effort. Besides, with this charged memory layer, the co-ion effort also can be inhibited. In this way, we can achieve a long range used. So when we further investigate the performance in the long-term operation, we can find both of these CNT and MCE can be used for more than 30,000 minutes. So the further mechanism for this, we can say during this process, the SPS result shows its structure was almost stable without obviously component changed. But during the process, we also found the production of hydrogen peroxide. With this process, with the production of this products, we can find the effluent DO was decreased while the concentration of the hydrogen peroxide was increased. So after the optimization of the SAC and the wider range, we want to see whether it can be really achieve the degradation of the organic pollutant. So in this way, in this reaction, in this study, we use is a sign reaction. As the H2O2 was produced, we want to know whether we can add some catalytic to directly convert it into the convert it into the function groups to achieve the degrade of the organic compounds. So in the anode, we added the biometric catalytic of the, and then in the cathode, we also added the catalytic to, we want to increase the produce of the H2O2. So this is a characterization of the collected and the electrode. We can see from the morphology and the SPS, we confirm the production of the preparation of these materials. And then for the electrochemistry, we found that the electrode really, the property of the electrode was really changed. Especially it showed a little higher point of the zero charge, which means it was more stable in this electro driving process. And then we use the 4 different organophosphorus compounds in this process from the HEDP and the EDTMP. And in the CDI system, which means we did not add the catalytics, or we did not supply the oxygen. We can find it showed a relatively low remove efficiency for these 4 compounds. And when we change the electrode, we can find the performance was increased. If we further added the oxygen in this process to form an eCDI, it showed the highest remove efficiency for all of these 4 compounds. So to explain this process, we first use the catalytic to do some electrochemical experiments such as the LSV. We found in this process both the CPZC catalytic showed a highest yield of the H2O2, and then we further to confirm this process in the eCDI system. We can directly found that the production of H2O2 was really increased. So for the further investigation, we try to see whether it really convert the generate H2O2 to the function groups. And we use the FTIR and the SPS result to confirm the hydrogen radicals production. And finally, we draw a schematic diagram of this process. We can see during the process, during this eCDI, the negative charged HEDP and other organophosphorus compounds will be collected on the anode. And meanwhile, the produced H2O2 will also be converted to the hydrogen radicals. And just around this, the anode, we can achieve the degrade of the organophosphorus compounds. And after the degradation, it can be directly absorbed on this anode. In this way, we can achieve the simultaneously degradation and the collection of the organophosphorus compounds. So this is a brief introduction of this process, and we use these 3 different research have shown that if we can further modify the anode and the cathode of the CDI, we can achieve the previous issues of CDI during the application. Moreover, we can further develop it into a electrocatalytic system, which not only can be used for the separation or the collection of the charged ions or the charged group. We can also achieve simultaneously degradation of these organic compounds. And we hope this can be used for the micropollutant treatment. So thanks for your attention.
Okay, thanks. So this is all for the first part of the afternoon session. So we will have a 20-minute coffee break. Thank you.